Hello everyone, welcome to the second lecture of Module 15 of the GPU Teaching Kit. This lecture covers the kernel optimizations for advanced MRI reconstruction. The objective of this lecture is for students to learn how to apply parallel programming techniques that we have learned in the previous lectures to the non-Cartesian MRI reconstruction. And we're going to go through the steps of determining the parallelism structure, and we're going to illustrate some loop transformations, and we're going to go through a memory layout transformation, and we're also going to cover how one can validate the results of a optimized kernel function. This slide shows the first version of the FHD kernel based on the doubly nested loop computation structure we saw for FHD at the end of the previous lecture. For the doubly nested loop, a very natural way of developing a kernel is to have each thread to compute an outer loop iteration of the doubly nested loop. So here we show that instead of having the outer loop, we have the kernel to first calculate the value of M based on the block ID and thread ID. So this allows each thread to pick up the work of one outer loop iteration or one particular N value of the outer loop. Once the thread has the M value, it can execute the two statements in the original outer loop iteration to calculate RMU and IMU. And then it goes in, all the threads will go into the inner loop, and the inner loop iterates through the pixels. For each pixel, each thread will calculate the contribution of the RMU values into the RFHD and IFHD value. This version of the kernel is very simple. It's very straightforward conversion from the sequential code. However, it has a serious problem. The problem is that when each thread calculates the contribution into RFHD and IFHD values, all of them are going to go through the same elements. They are all going to be doing read, modify, write into the RFHD and IFHD elements. And this creates a tremendous amount of conflict, and we will have to use atomic operation. But since all the threads are going to be iterating through the same N values, the threads are guaranteed to have conflicts. So all the threads in a warp will have guaranteed conflict when they try to do the atomic operation on these elements. So the performance is going to be very bad for this particular version of the FHD kernel. Now that we have seen the heavy conflict of the first kernel, we're going to need to do some transformation in order to reduce the conflicts. And this brings us to the loop transformation. The root cause of the heavy conflict or of atomic operations is because in the inner loops, all the threads are going to be all trying to read, modify, write the same RFHD and IFHD elements. If we reverse the order of the inner loop and outer loop, then N is only going to be changed in the outer loop, and M is going to be changed, iterated in the inner loop. So this effectively brings us to a situation where each thread, when executing the outer loop after that reversal, we're going to be able to have each thread to be writing into a particular RFHD and IFHD element. And the inner loop will iterate through all the M values, collecting all the contributions into that particular element for each thread. However, we cannot reverse the inner loop and outer loop roles if the loop is not perfectly nested. So here we see the original loop for FHD. We see that there are two statements. One writes into RMU M and one writes into IMU M. These two statements make the loops not perfectly nested. So we can perform a loop transformation called loop fission to create a perfectly nested loop. And this is what we show on the right-hand side. We take those two statements of the outer loop and create a loop of its own. And then we take the rest of the outer loop iteration, which is the for loop body, and we create a nested loop with in the second loop. And this separation of the outer loop body cannot be done all the time. It has to be only applied to an outer loop body where the first part of the outer loop does not depend on the execution result of a previous iteration of the outer loop from the second part of the loop. So in this particular code, the assignment of RMU and IMU to the M element cannot be dependent on the execution result of the inner loop from a previous outer loop iteration. In this case, because we don't change any of the R, phi, and RD values, we know that the first two statements in a particular outer loop iteration will not depend on the execution result of the inner for loop from a previous iteration of the outer loop. So that's why we can do this transformation. And after the transformation, all the RMU and IMU writes will be performed first. And then all the inner loop iterations will be performed in the second loop. So we are changing the execution order, but because the RMU and IMU assignments do not depend on any of the previous outer loop iterations, we are not violating any kind of constraint when we change the execution order of the RMU, IMU assignments versus the inner loop from the previous iteration of the outer loop in the original code. After we created these two separate loops, we can form the first loop into a kernel, and we will call it a compute mu kernel. And this kernel would calculate the M value, and then it will just each thread will just calculate one RMU and one IMU element. This is fairly straightforward. Now let's focus on the perfectly nested loop that we created as the second loop after loop fission. On the left-hand side, we show this perfectly nested loop right after loop fission. We still have the outer loop to iterate through M and the inner loop to iterate through N. Because we now have a perfectly nested loop, we can just reverse the role of the outer loop and inner loop so that we can have the outer loop to iterate through N and the inner loop to iterate through M. So this is shown as the right-hand side of the picture. These two code are identical, except that the outer loop and inner loop statements are exchanged. With the loop interchange, we can now create a second option of the FHD kernel. When we enter the kernel, each thread will calculate its N variable with the block index and thread index. And then all the threads will enter into the inner loop, which is iterating through the M variable. And within the inner loop, for each thread, the N value is not changed. And n value is calculated as a function of the block index and thread index. So every thread will have a unique RFHD element and IFHD element. So the thread is only going to be iterating through the RMU and IMU elements and keep accumulating into the same RFHD and IFHD elements. So because every thread is going to be accumulating into a different RFHD and IFHD element, there's no need for atomic operation. They're guaranteed not to conflict. So every thread is going to be sequentially accumulating more and more value into the same pair of RFHD and IFHD elements. Now that we have eliminated the memory update conflicts in the second FHD kernel, we can further improve the execution speed of the kernel by reducing the memory accesses using registers. So here we show the kernel code where instead of accessing the X, Y, Z, and RFHD, IFHD array elements in every iteration of the inner loop, we first load the X, Y, Z, and RFHD, IFHD elements into registers or automatic variables. And then when we enter the innermost loop, we iterate through M. And notice that the X, Y, Z elements are now accessed from the xn underscore r, yn underscore r, and zn underscore r automatic variables. So these accesses are going to be made out of registers. Furthermore, we're going to access the RFHD and IFHD elements from the register variables RFHDN underscore R and IFHDN underscore R. So the accumulation of values into these elements are actually done in the register. And then after we finish the innermost loop, we will write the final result of the RFHD element and IFHD element into their global array element. This can drastically reduce the number of global memory accesses in the innermost loop. So far, we have been accessing the k-space samples through the global memory. As it turned out, if we look at the innermost loop, all the threads are going to be accessing exactly the same k-space element in the same inner for loop iteration. What that means is that these elements, k-space elements, are perfect candidates for constant memory. If we access these elements through the constant memory, they will be cached, and the same value will be broadcast to all the threads at the same for loop iteration. And this can dramatically reduce the global memory accesses. So this is exactly what we're going to do. We're going to declare the constant memory versions of kx, ky, and kz that we are showing in the top of the slide. Remember that the constant memory is smaller, and so we cannot accommodate the entire k-space sample arrays into the constant memory. So we need to be able to take chunks. So this creates a for loop where in each iteration of the for loop, we take a chunk of x, kx, a chunk of ky, a chunk of kz, and we use CUDA main copy to symbol and copy that chunk into kx, kyc, and kzc. With the use of constant memory, we no longer need to pass the k-space data into the kernel as arguments. They can be accessed as global arrays, the global variables in C. So therefore, we no longer see these k-space samples in the argument list of the kernel. And inside the kernel, in each iteration of the for loop, we see that we're accessing kx underscore c, ky underscore c, and kz underscore c. I would like to encourage the students to read some more details about the constant memory for data layout optimization that will affect the performance of the code on some of the hardware devices. Now we will progress into the use of special hardware function units in the GPUs. As it turns out that the sine function and cosine function are very frequently used functions in GPU graphics code because of the various view transformations and so on. So the hardware actually has very efficient sine implementation and cosine implementation that has extremely high throughput. And these hardware implementations can be accessed through the interface, what we call the intrinsic function calls. And the intrinsic functions are underscore sine and underscore cosine. And we have already alluded to these functions in one of the previous lectures. So here we can convert the function call of cosine and sine into underscore cosine and underscore sine. The conversion of this function call will greatly improve the speed of the kernel execution because the hardware function units can produce the cosine and sine values at much higher throughput. However, it also can reduce the accuracy because the sine and cosine functions are implemented with limited accuracy as we described in the floating point lecture. So, we need to make sure that these, the hardware function units do not negatively affect the accuracy of the final result. As it turns out, the hardware function units actually provide sufficient accuracy because the MRI sample data are sampled with only a limited number of significant bits from the sensors, and so the limited accuracy of cosine and sine implementation actually preserves enough of the original data accuracy that we will not affect the final result, as we will see in one of the next slides. Now that we have highly optimized kernels using specialized function unit, as well as all the optimizations, it's important to show that the final kernel indeed produces results that are good for the application. So here we show a standard approach for validating the reconstructed image in the field of image construction. And here we show that we can calculate the mean square error and use the mean square error to calculate the signal to noise ratio. And using this formula, we can go. This slide shows the result of a validation experiment. We start with a true image, and we note this is the image that we would like to be able to reconstruct. And then we run an MRI machine simulation to generate the k-space sample data that would have been produced if we use an MRI scanner on this particular type of object. And then we reconstruct the image based on the k-space sample generated from that simulation. And we use the various versions of the reconstruction and evaluate the error produced by that reconstruction and then the signal to noise ratio produced by that reconstruction. We start with the gridded approach, and we see that the gridded approach produces a fairly high level of error and a fairly low level of signal to noise ratio, 16.8. Then we use the CPU double precision approach to reconstruct the image, and this gives us a much lower error of 12.1% and the signal-to-noise ratio very high at 27.6 dB. And we can see visually that this reconstructed image is identical to the true image, at least from the naked eyes. And then we use the CPU, but we reduce the precision to single precision. And as we expected, the single precision reconstruction maintains the error and also the signal-to-noise ratio. This is because single precision was sufficient in preserving the data accuracy, from the sensor. And then we start to use the GPU. The GPU-based code, the kernel that we use, will produce the same error and the signal-to-noise ratio as the single precision CPU code. And then we can use the register allocation and remove some of the global memory accesses. And we expect that this should not affect the result accuracy, and indeed it did not affect any of the accuracy, and it produced the same error and same signal-to-noise ratio. We did not talk about the GPU coalesce optimization, so we will not discuss number 7. And for number 8, we use the constant memory, and it should not affect the accuracy. So we would definitely be generating the same percentage error and the signal-to-noise ratio. When we use the fast trigonometry sine and cosine functions, the hardware implementation, we generate a slightly lower 27.5 rather than 27.6 dB, and this is a very acceptable difference. And so we would be able to use the hardware implementation. Basically, the hardware implementation is sufficient to preserve the significant values of the data generated by the sensors. With the optimizations, we can drastically improve the reconstruction speed. This slide shows the final reconstruction. If we look at the FHD column, the CPU single precision the reconstruction takes about 342 minutes. And if we look at the final GPU optimized code, we see that the reconstruction, the FHD computation only takes 1.5 minutes. So this drastically improved the FHD computation by 228 times. It's the combination of the parallel execution and also the special function units that are reducing the execution time in such a dramatic manner. Of course, the constant memory, constant caching is also contributing to that the improvement. With such a drastic reduction, we see that the total reconstruction is actually going to go from 343 or 344 minutes down to 3.19 minutes. The interesting observation is that now the FHD computation is actually comparable to the linear solver time, which is 1.69 in the final the reconstruction. So this is a classical situation where when we reduce the execution time of the most time-consuming part of the application, when the execution time of these originally time-consuming parts are drastically reduced, the parts that were not significant in the original application are now exposed as very significant portion of the execution time. So now the linear solver, after the optimizations, account for more than half of the execution time in the final optimized application. This completes the module 15 of the GPU teaching kit. Thank you.